Cool. So K, sometimes called spring constant, sometimes called stiffness constant. It's in units of newtons per meter. So for example, if we had a K constant equal to 100 newtons per meter, what that tells us is that that particular spring, every 100 newtons that we put on it, it'll compress 1 meter. Now, some springs aren't even, a meter long. Most springs aren't a meter long. But it's just saying if it were long enough and if it behaved ideally, 100 newtons would equal 100 meters of compression. Or if we were pulling on it, 100 meters of pulling would be 1 meter of stretching. So it's just a way for us to describe springs. So the question that you have, we've got a spring with an unknown stiffness constant. And we're going to solve for its stiffness constant by dropping a mass on it. Do we know how much the mass weighs?
Yeah, you just make whatever up. I just wrote down 100. I don't.
Okay, yeah, let's call it 100 grams. Let's call it 1 kilogram, just to have standard units. And then it was a 2 meter fall. Is that what I saw?
Sure. Again, I made all these numbers up.
Okay, so yeah, just making our own question. That's fine. So it's going to fall 2 meters.
And the spring I just put is 20 centimeters long.
Okay, and then I think I saw that you had it compresses 10 centimeters.
Yeah, when it hits it, it's going to go down to 10.
Okay, and so that's called, a lot of times you'll see that written as delta x, so change in x. So we can say delta x equals 10 centimeters or 0.1 meters. Cool with all that? This is your own custom setup, so I guess you're comfortable with it. So what we're going to do here is we are going to take a conservation of energy type of approach. And so what that tells us is that energy initial needs to equal energy final, because energy is conserved, right? You've probably heard that since high school science class. You can't destroy or create energy. So what kind of energy does this mass have when we're holding it above the ground? Potential energy. All of the energy in our system initially, so energy initial, is going to be whatever potential energy is stored in this block. And what's the equation for potential energy? It's fine if you don't remember.
I have it written down.
Mass times gravity times y.
Yeah,
Or sometimes you'll see an h instead of a y for height.
Yep.
So in this particular case, we know everything we need to know to solve for potential energy, so we can get an actual number.
So we have 1 kilogram, 9.8, and 2.
Perfect. So that's going to be 19.6, I think.
Yeah.
And what's the energy, or what's the units on energy?
Joules.
Good. So 19.6 joules. So after we drop this thing and it falls and it compresses the string or the spring to the maximum compression, so it compresses at 0.1 meters. At that instant, if we were going to take a snapshot when it's compressed right before it springs back up, what type of energy do we have in our system there? Potential energy of a spring. So our final energy is going to be all spring potential energy. Do you know the equation for that?
Do you want me to look for it?
No, it's fine.
Oh.
It's 1/2 times K
X.
Times X, or delta X, you might see, squared. So it's really similar to our kinetic energy equation, which is, so that helps people remember it sometimes, 1/2 mv squared. They're pretty much the exact same format, just different variables. Cool. So what we're going to say is our initial potential energy equals our final potential energy. So we can take this number and we can just set it equal to this equation, because we know that it needs to be, whatever this ends up being, it needs to come out to be 19.6 joules.
So 19.6 equals 1/2 K 10 squared?
Yeah, 0.1 squared.
Oh, okay. Can I use this?
Yeah, definitely. So 0.1 squared is going to be 0.01. 0.01 times 1/2 is going to be 0.05. So we're going to end up with 19.6 equals 0.05 K. To get the K by itself, we'll divide. And so that's going to be, I don't know, pretty...
Is it 0.05 or 0.005?
Oh, did it come out? Maybe I did the math wrong in my
I
mind.
think so. You can check. That's right.
Oh, I think you're right, actually. So 0.1 squared divided 2. Yeah, you're right.
So 19.6 divided by 0.005 equals K.
Yep. And so whatever that number ends up being will be our stiffness constant, or our spring constant, whatever we want to call it.
I don't know why. Okay.
So what did that number end up being? Just out of curiosity.
3,920.
Okay, so pretty big. 3,920, and the units on that again, newtons per meter. So this is a relatively stiff spring. We'd have to push with almost 4,000 newtons of force if we wanted to compress a full meter, or pull with that much force to stretch it a meter.
Okay.
Cool. Makes sense?
Yeah.
Oops. Good deal. Any questions there with that math or with that logic? Conservation of energy. You'll use this type of thinking all the time.